just some of the concepts of DFM, or design for manufacturing, that we're going to kind of focus on. And the principle here is that the data can be included in the drafting and design phases. And this is great because software nowadays is smart enough to pick this information up in the business systems, maybe an MRP, ERP type of deal, or the nesting or CAM programming side of stuff. And that is a key component to reduce time, reduce errors, rework, or even guesswork, where you have to take the time to go and ask the draftsman or the customer what was supposed to be going on here. You know, what I had something set up in this way, and I want to go ahead and read that in directly. So any portion of this where we can reduce that or eliminate that is what we target in smart software. And additionally, this might be kind of a gimme, but it is a good idea for the drafting phase, the engineers in that side of the business to understand capabilities of the machinery, as that helps guide a lot of the, I guess, the engineering of the part, and the idea that something can be modeled in one way, but maybe or may not be manufacturable, which is make or break as far as being able to make the part. It's tempting to believe that CAD, computer-aided drafting, is exclusive only to geometry. I mean, this is a principle that we'll look at here. And we want to just go ahead and not even go down the route of, well, there's an idea that making parts without errors is some kind of ideology. That's not real world. That's not what we're trying to say. It's just, you know, we'll move forward from there. So I did want to kind of talk about why this matters and why I care about it with just a very simple example. This is kind of an ideal world that I have this this bent part that my customer ordered, and somewhere in between there, the sales process takes place, and the part information, like the geometry and stuff, goes to the CAD's draftsman, and maybe that's in-house, maybe it's not. Let's say it's in, and they produce a 3D file that we need to figure out how to program the bend, the single bend, for this part, and that goes to the press brake programmer. So from there, he or she will take that and generate the G-code for running the press brake to accomplish this bend, and then a 2D file, a flat pattern, or something of that nature would be given to a laser programmer. And the laser programmer would take that and say, well, I need to cut that out of such and such stock. I'll nest it. I'll place it somewhere on the sheet. And that G-code gets handed over to the laser operator, who cuts the part blank. This is a physical piece that in your shop will get moved from the laser bed over to the press brake operator, who receives the flat part and then runs it on the press brake and ends up with the finished part. And I realize there's a lot of like oversimplification here, but this is probably one of the more straightforward flows or workflows of receiving a design, modeling it, creating NC programs to drive machinery, and end up with a finished item. This is a little bit more realistic. This is supposed to kind of replicate some of the problems that arise either upstream or downstream to get us to a finished part. And you'll notice there's a lot more steps involved to get us from part order to finished part. And I'll go ahead and break these down, and then we'll go ahead and look at some software here that we offer to help remedy or assist these problems. So the first breakdown we're looking at here is that the CAD model had some unknown material. So the press brake programmer is, I don't know what tooling's allowed here, the tonnage, the K factor to unfold this with, the bend allowances. There's a lot of information that's hinging on material. So he has to go back to the CAD draftsman. The information is put in the model, like maybe a property on the CAD file. It's like, okay, it's supposed to be mild steel, fine. Then the CAD press brake programmer knows how to deal with that. And there's an issue here because the K factor or the bend allowance that was used on the model differs, we actually need to generate a new 3D CAD file. So that process gets kind of interrupted, and there's a loop here where we have to go back and forth between CAD and the press brake programming step to get us a proper model. The CAD drafter might have their own bend tables. SolidWorks, Inventor, these kind of 3D CAD packages typically have their own information stored in there, so that when it's unfolded or the model dimensions are set in the CAD system, they may or may not match what the press brake software is using to unfold and consider tooling with. The second breakdown is that the laser programmer wanted to etch and mark bend lines for the press brake operator, but that was not given. So essentially, they were given a rectangle, and so there's no information with where the bend lines went or anything like that. So the CAD programmer gave the, or the press brake programmer gave the flat pattern to the laser person, and it's like, where are the bend lines? I need to mark them. So we go back to the press brake programmer, a new 2D file with flat pattern with bend line information and location and geometry is included in that. So the laser programmer makes a new laser program, gives it to the laser operator, and then gets a new flat part. So this does require the press brake programmer to recreate the flat pattern with this information so that the laser marking data is included. A third area of the breakdown in this is that there's no press brake tool for that bend. So this is very far downstream. This is right before we're trying to bend flat parts, the blanks. And this is an example of a really bad issue where we actually have to scrap stuff because the part that was cut by the laser is not the right size, because I actually have to pick a different tool. The press brake programmer generates a new program with the right tools, and the press brake operator eventually will receive the new flat part blank. But the one that was cut earlier, it's the wrong size. And so for the tool that we're using, it's that information just has to be carefully matched up so that by the time we're bending the blanks, that the right tool and geometry and all that stuff is included in there. So, I mean, there's tons of variations of this. You may experience none of this or all of this and more. For example, other situations with different kinds of parts can arise. For example, if you've got bevels and interpreting maybe on a 2D drawing, like a AutoCAD drawing file, that we're doing bevels here, or the text is a big one too. I want to include the fonts that I want. I'm either just marking them on the parts, or I'm just using them as detail for reports later, or what is the purpose of the text that was included with the drawing file. Additionally, processes, this is talking about machine processes, that this contour should be treated with this tool or this process. Either that's mapped in correctly because the laser, plasma, oxy, water jet, whoever the machine programmer is, didn't know about that request from the CAD model. It's just geometry, so the programmer just does what they do best and adds process information. Additionally, it could be included just to avoid the need to even have them be involved at all. Automatic tool pathing is a key feature to reduce time, and if that information can be just attached to the geometry or the part, then there's no need to look that up or select from a list or repeat this process for many, many parts. Is just use that information as is. Grain is also a consideration, maybe. If you're nesting parts on maybe just plain steel, grain won't matter as much, but for router and wood applications, it's a big deal. So to include that grain direction and setting that in a way with the model, so that the nester isn't just putting them all in different random directions, that we are keeping the parts along the grain or against the grain, or maintaining some angles there. Additionally, bill of material organization and just being able to capture a list of parts with set quantities allows for reuse in the future, that if I need to pull a kit and cut 6 of these boxes or the 6 of these products, that I don't need to re-import, that I don't need to reconfigure. reuse information is just set for me in a bill of material, and we can capture that when assemblies are brought in to nesting. Additionally, naming the parts, naming the cut list, naming the items that are contained inside of our assemblies when we're dealing with multiple parts can help us to differentiate and filter, which equates to speed, equates to smartly including and excluding what we are going to try and manufacture in maybe the laser process, but not deal with nuts and bolts and glass and plastic in that process step. So we can, knowing that up front, we can kind of be a little bit smarter about how we design our parts and name them to make use of that. You know, if you name your assembly part 1 and you've got all the way up to part 999, they may or may not all be the same kind of part or all need to be brought in. And then configurations as well is a key feature for CAD modeling in general, where you can have multiple versions, lengths, just like the word says, configurations of an item, and possibly doing some things there to maybe say, these are what I need to manufacture, these are the full assembly, and yeah, just being able to include some of that. So what we want to do now is get out of this presentation and jump on over to SigmaNEST. All right, so we'll go ahead and start with importing in a few parts that kind of cover a variety of these situations that we mentioned here. So let me go ahead and turn on this filter and go into configurations. And I've got an assembly here. Let's go ahead and just open this up in SolidWorks. So this assembly has just a plain assembly with a few different parts, but it does make use of configurations here where I've got maybe a 10-inch, 8.5-inch, 6-inch variation. Some of the parts are bent, so bend lines are another thing that we mentioned in our example that we might want to capture. Another thing to pay attention to here is even the material of the parts that we've got in these assemblies may or may not be set. These examples are not set, but if they were, how we're unfolding those and what information we're using to unfold those is key. So we have a way to capture the name of material and equate it to something in the CAM programming side of it, into SigmaNEST. So we'll go ahead and do that here. We'll go ahead and grab this assembly, and I want to show before we alter any mapping for that. So I'll just use this. Configurations, there we go. So what I'm doing here is I have a group of settings for the SigmaNEST SolidCAD desktop, which is our 3D import module, that is saying this is the configuration I want to pull. I know from engineering that there's different configurations, but the one I need to cut is this one. So I can just specify that name here and bring that in. The material that we're going to capture there probably is going to have some issues with it. So I wanted to point out how to deal with mapping that to something I can cut at the time of import. We can do that automatically. All right, so we're just processing that. Some filtering has taken place. The nice thing about SolidCAD being able to go in and see all the different configurations, which may or may not be possible in other kinds of programming software. So I'm getting these errors here because I'm noticing the material that was set for this part specifically is some, I don't know, is it whether that was the engineer's idea of making things more informational or including some other stuff. I could have had him map that over in this way and say, well, that information is useful, but I want to make use of property mapping and say, well, you set that up in SolidWorks under maybe the part properties somewhere. So I can go in and say, well, these are properties, and I can have some of the fixed properties that are included with SolidWorks, or I can actually set up custom ones and then map this over into the SigmaNEST part. But he didn't do that. He or she just set the materials, and actually if I look through the variety of other ones I've got here, these are just seemingly random. I can't cut these. The technology tables that I'm using aren't aware of how to deal with this. So mentioned that we can map that over. So I was just going to show P code file in my SN data. I can open this up and just, I already had this set up here, but I'm just going to add in the name of those materials separated with a comma on the material that I do want those to be renamed as. So for example, the first material that I was pointing out, that's equivalent to mild steel for maybe the cutting parameters, so we can just use those. So I'll re-import here. And just to look in some of the rest of this, I've got other names that I have in my CAD system, like SolidWorks. They have an extensive material library, which is great. But for cutting purposes, I may or may not need to know that this is all the name of the material I need. I just need mild steel, or possibly the name of the material is also telling me the thickness. So I can do that as well. For example, this is reading as 1/4 inch 50A. The material can be split into the SigmaNEST material name and then the cutting thickness as well. So if I go over here, you'll notice there's no errors. It's great because, again, I chose to map over those SolidWorks materials to ones that SigmaNEST knows how to handle and cut, and that's great. Additionally, the bend lines were brought over. There's options here in our configuration to mark those or keep them as like detail notes where they're not cut. They just might show up on the reports. They're great for maybe dimensioning. I can throw in a dimension saying this bend line is here, and so on. Let's move on over to another example of filtering where I can make use of desktops that we've got. Looking for the CNC table, go to the assembly. All right, so this SolidWorks part has a ton of stuff in it. Let me go ahead and start importing here, and I can go ahead and explain a little bit of this. The part itself, so I should say assembly, has quite a large number of unique pieces to it, including non-items that I want to process for sheet metal. That is like nuts and bolts, the engine for or the motor for the actual router portion of this. So these are things that I don't want to include, and in the SolidWorks configurations, I can essentially filter out anything that's not needed for that. So now SolidWorks did not like that. We'll go ahead and close that. All right, let's reopen it. Okay. Yeah, so I won't open it in SolidWorks. We can see here that we've got some nuts and bolts. This I do not want to include components of the engine assembly, but we do have set up in there on that configurations for that assembly. Let's see, let me pick this one, get that going. So we've already either suppressed or excluded out of maybe the manufacturing configuration of this assembly things that I don't want to include. And that's great because I have the flexibility as a draftsman to either do that, set up a separate configuration, or suppress or delete or set up another variation of this that I only want the Plasma programmer to see and deal with as far as the programming level and nesting side. Additionally, in that configuration, we had excluded some items by name. So we mentioned that if we name things with some intelligence or some convention, we can pick that up at the time of importing and just exclude out of them. And the other option that we had on, I'll go ahead and cover this again once it completes and imports here, is creating a bill of material of this assembly, maintaining the quantities of each part. Okay, so we've got this in here, and we have our materials mapped over. That's all great. I have a comment that was also mapped over from the SolidWorks property mapping. And then if I hop over to the BOM, there is the bill of materials that's showing me there's 21 unique parts, and just total pieces wise, we've got about 28. And so the nice thing about this is if I want to load this in the future, I can just hop over to the BOM, grab this, load in 6 of these, and just continue with the rest of the programming process that is like nesting and task creation and reporting for these components. So that's nice to be able to just do that quickly and reuse that. I mentioned some of the mapping options in there, so I'm just going to show you really quick here in the configuration how to get to that. So from SolidWorks, we can pull some of the default options, but if I had a custom option, this is where I would specify the name of that property and then what that equates to when the SigmaNEST part is created. And yeah. All right, so another recognition item that is great for design for manufacturing where I don't necessarily have to add in a lot of guesswork for the programmer is adding in bevels. So we can define bevels with a part. Like this one here, we've got a blind bevel, knife, and a Y. There are some bends as well. We can bring this in, and from the SolidCAD desktop, if I switch over to this desktop, I've got it so that the bend lines are coming in as no cut, so they will just be present but not cut. And then this bevel recognition with a fairly sized tolerance. This is a nice item that has been added recently to capture what the bevel should be within a certain tolerance, so it's not have to be exactly 1-to-1. So you can reduce that tolerance if you need that. The part will come in, the bevel attributes will be assigned to the part edges, which is useful for, again, taking a part like this and cutting it. One element that helps with this is to, again, have the model contain the bevels, but if that's not the case, we do have support as well for importing in drawings that have this annotation included as well. So here's a drawing file. I just open really quick. That has some knife bevels defined. Not really, I cannot, this is a 2D item, so I can't say this edge is going to be, beveled, but I can include some annotation or some text, and you can see the association here with the AutoCAD group, that this text is grouped with this edge. So by doing that, SigmaNEST can interpret that and bring that in. So I'll import this. Interactive mapping just shows the geometry that was going to get included with that. And there's our part. And then there's the knife bevel assigned there. You can change the text here. It may be the syntax or the naming convention isn't what you use, but in the configuration we can set what that will get interpreted as. RV is a bottom knife, 45 ending in 45. The direction that the line is drawn in CAD will help dictate if this is a variable bevel. So the start and end variable bevel properties that SigmaNEST supports can also be added on the 2D bevel import feature. Another item to mention here is text. We talked about text, where text is great. People go overboard with it in that we can have nice fancy text. You can use Comic Sans, you can use Wingdings, you can use practical text like maybe Arial like this. And if we bring this in, here's the part geometry, here's my text. And if I set this to say I want to mark it, like this is the customer wants to go ahead and annotate this with my laser, and I'm thinking this is all great. However, I'm going to go ahead and add some NC to this, and we'll just hop on over to simulation and note that there's a lot of cutting going on here that maybe this is the aesthetic look that's required, and that's fine. Just know that it will produce a lot of code and might take a while depending on exactly what is being etched here. But having the 300 so marking lines just to annotate this part, maybe the unloader is going to stack these and I want the work order number, or I want some kind of helpful job shop information on here, then this kind of text is just unnecessary. So if I go over and grab what we call an Shx font, just to look at this again, Shx fonts are different than TrueType in that they were designed to be as lightweight as possible, and you can see that it's not as fancy looking. And the nice thing about including these kind of fonts, I guess, with the part is that when we do the same thing here and say, well, I'll mark this and bring this in. The machine processing, it's much easier to handle this. You can see that there's just a few lines here for this S and then going to there. So that's great. That's just a hint or a tip that we found that possibly you weren't aware that SHX fonts are a thing, and in AutoCAD they are indicated with a different icon. So being able to support that on this side, that I want the artistic fonts or the other one, or the I guess the more manufacturing-oriented marking fonts is an important distinction. And if you don't want the conversion, the option here to say I want to use the SigmaNEST included fonts is also available at this time. I wanted to point out some of the handling or ways to handle some errors that occur that just are bound to occur that have been added recently with X1. So I've got, let me go ahead and just create these parts as maybe these are from some customer and unfortunately they didn't name their DXFs with the problems that are contained in them, which would have been nice. But I'll import these and we'll note a couple things. I get an error, it says what's up here. So I've got a duplicate entity, and I don't know if you can kind of see it there. The color is changed over that. There's an open contour where there's actually a gap right here. And then we've got what we call a slit cut geometry that's occurring on these corners here. So I wanted to go ahead and show that manually I can go in and intervene with this just fine. I can go in SigmaNEST and pop open to the part geometry. Verify geometries here. I go ahead and select everything and say I'm looking for duplicates. Go ahead and delete those. So the errors were found. There's a little bit of a points indicating where the geometry problem was. I can rebuild this. Hold on, maybe I didn't hit apply. Let me go ahead and do this. Okay. I think I have the wrong entity type here. Let's go ahead and fix that. Yeah, it should have been curve cut. Okay, so let's do that. The open contour, depending on the kind of open gap that we have here, there's going to be some CAD tools here to maybe say I want to trim and extend and close that up. That's easy enough to find. And the slit cut example is having, let me go ahead and change this all to curve cut. And then if I close this, it will complain that those entities are open, they're interfering with another contour. So in verify, I can go ahead and say, please help me find these. Maybe they're not as obvious as with this part. I can say, well, my slit cuts should be, I don't know, marking. I'm going to mark those. So they're highlighted. I can change their color. But the main thing is that the attribute associated with those slit cuts are properly picked up. And if I go over to marking, they come that way. But that's all great. Anyone that's used SigmaNEST for some amount of time probably is familiar with how to clean these things up manually. The idea is to train the software and use settings and parameters to help deal with this in a more automated way. So I did want to point out that I've got a desktop mapping import desktop that is able to go ahead and take these and bring these in, and you'll note that the same DXFs are repaired automatically. I have the same mapping, the same closure, the same removal of a duplicate. with these new desktop mappings. And just to kind of show that, let me hop over here, go to interactive. And then it's from this screen that repair geometry can be associated now with a SigmaNEST desktop. And I can say I want to do this and this and this and this, and then seal up gaps, replace or remove duplicates, and so on. So that's definitely something to check out if you're having to deal with problematic geometry frequently. So there is that. I also wanted to show a little bit about our interactive unfolder. This kind of involves a little bit about the bending process and some of the unfolding issues that we mentioned in our example earlier, where I go in and hop on over here, unfolder. So I've got these sheet metal parts. This is a part of the new SX module that's with SigmaNEST X1. I can say, well, let's go into this part. I'm going to unfold this now with some K-factor that's pulled from my SigmaNEST database. So the bend radiuses that I've got here are all coming from the, I guess, this material that has a K-factor associated with it. Same with, I guess a better example is this, because I can measure it from here to here. It's 20.84 inches, and that's all great because of the K-factor picked up with this material. I can go in here and say, well, that wasn't the proper K-factor on that bend. I need to change it by, and then you can see the growth of that bend region, and okay, that's nice. So I can come in and interactively deal with sheet metal unfolding from the programming side. The main reason that I want to make sure that this is happening correctly is that when we send this over to the press brake programmer, that they receive a properly sized blank, and the physical part that was cut out on the shop is also going to match what needs to get bent physically on the machine. So these are the bends that came with the flat pattern that we had generated here. So I can unfold the rest of these, send them over to SigmaNEST. And then the problem I wanted to highlight was if I go into that part we looked at, this one here, those are step files, but if I had been working with a, say, SolidWorks sheet metal part, the sheet metal information that's maintained in SolidWorks can be different than what's used on the SigmaNEST side. So I had unfolded and imported these blanks with the SX module, the unfolder module, got my bend lines, and that's all great. And then if I again just measure this guy with the bend radius that I had used, there's that. Additionally, over here, go into here. Let me actually go to bends. That's not that bend, this bend. So the bend radius used here is based off of the material that was set on the SolidWorks part, or possibly a custom one. So there's just wanted to point out that differentiation, that what is set for SolidWorks and then the flat pattern that it has is what SigmaNEST will use when you have a sheet metal part. So if this is not a sheet metal part, it'll do its best to unfold just the 3D body. But because this is sheet metal and because I have a flat pattern, it is assumed, since that was what was included with the part, that is what is intended to be manufactured. So it's just important to note that the unfolding bend parameters that are used for this sheet metal part in SolidWorks are maintained and correct with the other systems as well. So that is why the SX side of SigmaNEST is trying to work on controlling this, maintaining a database, and integrating with the other systems to ensure accuracy throughout the process there. One of the other last things to mention is with the router information. I can go ahead and clear this out here. before SolidWorks. Then I had a router part. I need the assembly. All right, so the wood chair, I had added a sketch in here that had a specific name, and I just wanted to point out that we could define in this area of SolidCAD settings information from my router that I want to say that this sketch should receive this tool or router tool, or it could also be like Plasma or a marking process for profile cutting, but I can do that mapping here, as well as maybe that it needs to be cut or it needs to be marked. It's a maybe everything on this sketch is just detail information, possibly setting the contour direction if it's closed. So that information can come through as well, and is handy especially if I have a cut that requires maybe multiple passes and I want to associate different tools to those contours. That can be done with sketch and process mapping as well. We'll import this. And if you guys have some questions on anything that kind of shown so far or whatever, go ahead and start thinking about those. We'll have some time at the end here to answer any of those that might have come up. So there's the assembly, there's the sketch that I have, and so if I went in and nested this with the router machine that I had, the tool that I had mapped over would go ahead and get associated with that part there. Let's see, out of everything we had talked about, I think that was more or less what we were hoping to go through. Is there anything that I can clarify or show or explain with a little more detail regarding some of the import stuff and how a lot of this transferring from CAD to CAM can be assisted with the right settings, the right software feature to assist with that? Okay, well, if there's no questions at this time, that's okay. We'll go ahead and I'll pull up in the contact information that we've got here, whether it's through the main line or our website. And then just a reminder to go ahead and stop by our booth at FabTech. It's at Chicago this year from November 6th through 9. We're booth A4442. And I'll be there. So if you have questions there, you can also just save them and we can talk in person. So I wanted to thank everyone for joining today, and yeah, have a good one.